Okay, so we've talked about arrays, we've talked about pointers, we've mentioned that the name of an array is actually just a shorthand for the address of the initial element of the array. So an array is, in some sense, really a pointer, and a pointer can be used as an array because the subscript notation is simply syntactic sugarcoating for adding an offset to the pointer and then doing a dereference or an indirection on the resulting pointer. In this lecture, we're going to take another look at arrays and pointers, namely when we pass arrays as arguments into functions. We're also going to see more detail about C-style strings and how you can pass strings into a function and manipulate the characters within a string. And at the tail end of this lecture, we're going to take a look at how a C++ program interacts with the memory on your machine. Okay, these first couple of slides repeat the tail end of what we talked about in Lecture 6, so I'm not going to repeat this stuff, except I can't resist repeating that arrays are really pointers and pointers are really arrays, and you can use them interchangeably. When you pass an array as an argument into a function, what you're really passing is a pointer to an element of the array. Generally, that's a pointer to the initial element of the array. Here I have this program in which I have A declared as an array of 4 ints, and those ints have been initialized with values 1, 2, 3, and 4. I'm going to call a function triple, and I'm going to pass A as the first argument to triple. Well, A, as we just got done describing, is really the same as the address of A sub 0. That means that that first argument is really simply an address. It's really simply a pointer to an int. There's no information inherently in that pointer that indicates how long that array actually is. So in C++, we're going to need to pass the number of elements in the array as a separate additional argument into the triple function. All right, so the triple function is going to triple the values in A. We'll see how that works in just a second. But A will be modified by this triple function to 3, 6, 9, 12. And then this for loop, after triple returns, is going to display those new values. Now, I'm using an integer subscript called I to step through the items in that array A after triple returns. Notice that in C++, I can actually go ahead and declare and initialize the data type of my loop variable right inside the initialization expression of the for loop. This is very often done because often when you arrive at a for loop, you haven't yet previously defined a loop variable to use, so you can go ahead and just declare it and initialize it right there. This also has the benefit of making the so-called scope, that is the region of code in which this variable I is visible. The scope of this variable I is limited to the for loop itself. So it won't conflict with any other variable called I that might exist in this same function either before or after this for loop. Okay, so let's take a look at how this triple function can be written. The naive way, the beginner way, let's say, of implementing the triple function is to declare the parameter to be exactly the same type of thing that is being passed in. All right, so if A is declared as an array of 4 ints in main, we can declare A here to be an array of 4 ints as the first argument, and then after that we're also specifying the size, that is the number of items within the array. And what this implementation is doing is we're setting up a loop variable I, initially 0, just like we did in the for loop in main on the previous slide. And we're saying as long as I is less than the size, that is, as long as I is less than 4, modify a sub I to be 3 times its original value, and then add 1 to I. So this will loop through and change, as I said, 1, 2, 3, 4 to 3, 6, 9, 12. Now, even though I have declared this parameter a as an array of 4 ints, the 4 is, in effect, has no more meaning than like a comment, because what's really being passed in there is just the address of a. So it's more common for experienced programmers to just indicate, okay, this first argument is an array of ints, and just leave out any mention of the size. The advantage here, of course, is that this function will work with arrays of 10 ints and arrays of 2 ints and arrays of 1,000 ints, as well as it will work with arrays of 4 ints, because we have specified the number of items that there are, the number of elements that there are within the array. As yet another alternative that's completely equivalent, and in some sense this is what's really going on, we can just say, all right, a is a pointer to an int. That is, a is the address of some int that we assume is in some array somewhere, and we can use our pointer as an array by using the subscript notation rather than saying star of the quantity a plus I. All right, so all 3 of these implementations that I'm showing here on slide 7 are exactly equivalent to each other. There's really no difference between them as far as the compiled code that the compiler produces from these. Now, we can also have what we would casually think of as multidimensional arrays. In C++, actually what we're doing here is creating arrays of arrays, or arrays of arrays of arrays, or arrays of arrays of arrays of arrays. And here is the notation that we use for doing that. In this little program on slide 8, this A is an array of 4 things, and each of those 4 things is an array of 2 ints. So I have initialized this array, and I have one pair of curly braces containing the entire collection of 4 elements that A contains. But each of those elements that A contains is, in turn, an array of 2 ints. And so I have nested curly braces here, in which I have the 2 int values that initialize each array of 2 ints within this array of 4 arrays of 2 ints. So that's a little awkward and complicated to say. Notice the way that I'm reading this. I start by saying the name of the variable, and then I read the array subscripts and sizes to the right, and after I've hit the final dimension of the array, I go back to the left and read the data type of each of the elements. So A is an array of 4 arrays of 2 ints. Okay, A is an array of 4 elements. Each of those 4 elements is an array of 2 ints. The name A, the name of any array, is the same as the address of the initial element of the array. But the elements of A here are actually arrays of 2 ints. So technically the data type of A here is pointer to array of 2 ints. That is, if I start at the address A, that is the pointer to the initial array of 2 ints, and I add 1, what I'm going to get is the address of the sub1 element of A. Since each element of A is an array of 2 ints, and since each int is 4 bytes wide, the numerical value of A plus 1 is actually 8 bytes in memory further along from A itself, that is, from the address of the beginning of the array A. Okay, so I'm going to be stressing the importance, for being a highly skilled C++ programmer, of paying very close attention to the data types of your objects at all times. It is correct to say that A is an array, and it is correct to say that A is a pointer. But although that's correct, it's not enough information for you to fully understand how to use A. To be accurate, we have to say that A is an array of 4 arrays of 2 ints. That's very different from the A that we had previously, back here on slide 6, where this A was an array of 4 ints. Okay, an array of 4 arrays of 2 ints is a very different beast from an array of 4 ints. And A itself we can think of as being a pointer to an array of 2 ints. Okay, here are implementations of this sumfunc function that is receiving A as an argument. So in the first example, I'm using the naive representation of A. I'm declaring that A is an array of 4 arrays of 2 ints, and that works fine. But really, the size, this dimension 4 here, is really just kind of like a comment. I can leave it out and say that A is an array of some number of arrays of 2 ints. And the size here is the number of items in that array of arrays of 2 ints. Or, rather than using the syntactical sugarcoating of the array notation, I can say that A is a pointer to an array of 2 ints. And all 3 of these implementations of sumfunc are exactly equivalent to one another in terms of the code the compiler generates. Now, array notation has higher precedence than the indirection operator with star. Consequently, the parentheses that I've used here around star A are vitally important. If I left out those parentheses, rather than A being a pointer to an array of 2 ints, A would instead be an array of 2 pointers to ints. Okay, so the meaning of A is very different depending on whether you do have the parentheses, which in this example are absolutely required, or whether you don't have the parentheses. Okay, let me back up to slide 8 here and show some diagrams of this array so that we can talk about how to access various elements and how to understand various pointers into this array. So here is my array A. A is an array of 4 things. The blue here, I guess, is a little unfortunate because the blue looks more pronounced than the red, but each item, okay, is an array of 2 things. There I've clumsily underlined the first array of 2 things. And here we have the second array of 2 things. And here we have the third array of 2 things. And each of the things in these arrays of 2 things is an integer. A is the address of the first element within this array of 4 things. So A is the address of the first array of 2 ints. A plus 1 is the address of the second array of 2 ints. A plus 2 is the address of the third. A plus 3 is the address of the fourth array of 2 ints. To access individual ints within this array of 4 array of 2 ints, I can use double subscripts. So A sub 0 is the first array of 2 ints. A sub 0 sub 0 is this particular int value, which is 1. A sub 0 sub 1 is the int immediately following A sub 0 sub 0, and so that's the 2. All right, so those are the initial values of the 8 integers. When I call sumfunc, what's going on in sumfunc is that A sub I sub 0 is having 3 added to it for each value of I going from 0 up to 4, up to but not including 4. And A sub I sub 1 is being replaced by its negative. So the 1, 3, 5, 7, which are A sub 0 sub 0, A sub 1 sub 0, a sub 2 sub 0, a sub 3 sub 0. Those are all having 3 added to them, and they become 4, 6, 8, and 10. The even-numbered integers in here, a sub 0 sub 1, a sub 1 sub 1, a sub 2 sub 1, and a sub 3 sub 1, all get changed to their negative. So we're going to get negative 2, negative 4, negative 6, negative 8, and that's what we see happening after this sum function returns. All right, a little bit more subscripting gymnastics here. Remember that C++ does not do any array bounds checking. So A is an array of 4 arrays of 2 ints. A sub 0 is actually the address, technically, of the first array of 2 ints. A sub 0 sub 0 is the 1. A sub 0 sub 1 is the 2. A sub 0 sub 2 is guaranteed to be the next integer, 3. Why? Because remember that in C++ it's guaranteed that elements in an array are laid out in ascending contiguous memory locations. So it's guaranteed that the int 1 will be the first thing here, and that will be immediately followed by the int containing the 2. That in turn will be immediately followed by the int containing the 3, and then the int containing the 4, etc., and so forth. So way out here at the end, I can access the final element of A as A sub 3 sub 1. Okay, A sub 3 is this array of 2 ints. A sub 3 sub 1 is that second int in that array of 2 ints. But I can also access that thing as A sub 0 sub 7 by just relying on the contiguous ascending memory locations of the elements in an array. Here we have a couple more somewhat similar examples. All right, A sub 2 is this array of 2 ints here containing the 5 and 6. A sub 2 sub 0 is the 5. Now, again, we don't have any bounds checking going on, and it turns out that C++ allows me to use negative subscripts. So if this is A sub 2 sub 0, then A sub 2 sub minus 1 must be the 4. A sub 2 sub minus 2 is the 3. A sub 2 sub minus 3 is the 2. So A sub 2 sub minus 3 is 1, 2, 3 ints worth of memory before A sub 2 sub 0. Now, if you made the mistake, remember that A is an array of 4 arrays of 2 integers. If you made the mistake of accessing the element A sub 4 sub 2, forgetting that the subscripting goes from 0 up to n minus 1, well, that element, A sub 4 sub 2, exists in memory, but it's actually 3 integers past the end of the actual memory that's been allocated for A. Okay, the first 2 ints are, this is A sub 0, then the next 2 ints are A sub 1, A sub 2, A sub 3. This is A sub 4, all right? But this int here is A sub 4 sub 0, and then we have A sub 4 sub 1. And so this int here, which is 3 past the end of the array, is the int A sub 4 sub 2. Okay, so the lesson is that everything here is completely predictable, but you have to understand the rules very well. Okay, so moving on to slide 11, I mentioned that these parentheses around star A are extremely important in the sumfunc implementation. The parentheses make A be a pointer to an array of 2 ints. Without the parentheses, A would be an array of 2 pointers to ints. All right, so here we have a focus on that distinction. Because of the parentheses here, this notation says that P1 is a pointer to an array of 2 ints. Now, P1 is a variable. It is going to occupy memory, and it is going to contain the address of some array of 2 ints. Now, in this declaration, notice that P1 is not initialized. So P1 just contains some random pattern of bits. But the compiler is going to treat that random pattern of bits as the address of some array of 2 ints. Okay, so in my diagram here, actually let me move slide 11 over to the left here so that I can show my diagrams on the right side. All right, so here's P1. P1 is uninitialized, but it does contain the address of something. So wherever P1 currently is pointing, the compiler assumes is an array of 2 integers. And if I add 1 to P1, then I'm going to get the address of this next array of 2 integers, and so on. If I leave the parentheses out, then the subscripting notation takes precedence over the pointer notation. So without the parenthesis, this says that P2 is an array of 2 things, and each of those things is a pointer to an integer. So here is how P2 looks. P2 is an array of 2 things. Each of those things is a pointer to an int, and that array is not initialized either. So we have basically a couple of random pointers to ints in P2. However, they do point somewhere. So we can imagine these random pointers pointing off into memory someplace. And so they point to an int. If we add 1 to the pointer, we get a pointer to the next int, and so on. All right, so that takes care of our discussion of what happens when you pass an array as an argument into a function. What you're actually passing is a pointer to the first element within the array. Next, we're going to take a look at C-style strings. A C-style string is an array of characters. It always has a length of at least 1. It ends with a null byte or null character, and that is the character whose integer value is 0. As a char, we write that as quote \0 quote. So it's another one of these special characters like quote \n quote for new line, quote \t quote for horizontal tab. Quote \0 is the null character. And because a C string always ends with a null character, this is why it's always of length at least 1. Okay, when you write a string literal in code, when the resulting compiled program is executed, these string literals get loaded into memory as arrays of chars. Now remember, an array of char is essentially like a pointer to a char, and it turns out that in the location of your code where you wrote the string literal, what you get from the compiler at that point is a pointer to the first character within the string. So, here on slide 13 is an example. In this program, we have a string literal, hello, new line. That occupies 7 characters, 7 chars, 7 bytes worth of memory. H-E-L-L-O, new line, and then the null character that the compiler automatically adds. When I give a string literal as an argument to cout, what's actually being passed to cout is the address of the first character in the string, and cout understands that it should display all of the characters within that string up to, but not including, the null character at the end. So when I run this code, this first cout statement displays hello and a new line. In the next statement, I'm declaring P as a pointer to a char, and notice that I've initialized P with this string literal. Now, it's not guaranteed, but generally speaking, if you have multiple identical string literals, the compiler is smart enough to figure out how to arrange for that to just be one copy of the string literal. So here we can assume that P is pointing to the little h at the beginning of hello. And when I display P with cout, well, in this case here, when I displayed hello, what I actually was passing to cout was the address of the h. And in this case down here, where I'm passing P, I am likewise passing the address of the h. And so there again, hello is displayed on the screen. In terms of diagrams, here's what's going on. I've declared an initialized P to point to the H at the beginning of the string literal hello. So, hello is first displayed directly, then hello is displayed through P. Next we have an array of char called A. It's an array of 7 char, and we've used array initialization notation to initialize those 7 chars with HELLO new line null. Now, because this char array does have a null character at its end, it is a C-style string, even though it's not in double quotes. So when I display A here, remember that the name of an array is the address of the initial element within the array. So in this case, little a is the address of the H, and this also displays hello. Now it's displaying this copy of hello rather than this copy of hello up there. Now a string literal, it turns out, can't be modified. We will talk about that in more detail later. So if I attempted to actually change some of the characters in the string literal, I would get an error at runtime and my program would die. But the same is not true of a locally defined array of chars that happens to have a null terminating character so that I can treat it as a C-style string. Consequently, if I say star A gets J, that does actually replace star A, that is the first character in the array, with a J. So now I have Jello, not quite correctly spelled, in the array rather than hello. And this final cout statement displays Jello on the screen. Okay. Next up, we're going to take a look at a couple of operators that are used very commonly with pointers. The increment operator and the decrement operator. Increment adds 1 to an object. Decrement subtracts 1 from an object. Now the question is, when does the addition or subtraction occur? And it turns out that it depends on which side of the object you type your increment operator or decrement operator on. If you type the plus plus after the name of the object, this is what's called a post increment, and it causes the object to be incremented by 1 after the original value of the object has been used in the statement. On the other hand, if you put the plus plus in front of the object, this creates what's called a pre-increment, and it increments the value of the object before the resulting modified value is going to be used in the expression. Now, it turns out that when we're using increment or decrement to step through elements in a string, post-increment or post-decrement is much more commonly used. Let's take a look at an example. Here I have a program in which the main function calls a function DisplayStir. In this example, we've defined the DisplayStir function above main so that the compiler understands what the interface to DisplayStir looks like before DisplayStir is called. The argument to DisplayStir is a string literal. Now, because I have this string literal in my code, that means that memory is allocated for this unnamed array of 7 chars, HELLO new line null. And what I get at the point where I wrote hello in double quotes is the address of the H. So it's actually the address of the H that's being passed to the DisplayStir function. When the DisplayStir function gets called, its parameter is allocated in memory and initialized with the value passed in. Okay, the value passed in is the address of the H. So I now have this situation. The variable s in the DisplayStir function has had memory allocated for it, and s has been initialized to point to the little h. Within the body of the DisplayStir function, we are saying WhileStar s. That is, we're going to do something over and over again while this star s test succeeds. Well, okay, in C and C++, false is equivalent to 0. Any kind of 0 is treated as though it were false when you're using it in an if or in a loop. So in effect what we're asking here is while star s, that is while the value of the thing that s points to is not 0, perform the cout statement. Let's see, at this point, what is the value of star s? Well, the value of star s is the little h character, and we know that the little h character does not have a value of 0. The only character that has a value of 0 is the null character. We could look up in our ASCII table to find out what the actual value of little h is, but all we really care about is that it's not 0. Okay, so since that value is little h and not 0, that means we're going to execute this cout statement in which what's being displayed is this expression star s plus plus. Now, the plus plus there is being used as a post increment. That means that the plus plus does not take place until after star s has been displayed to cout. What's the value of star s? Well, the value of star s is h, so h is displayed on the user's screen. After h has been displayed on the user's screen, then we bump the pointer, and what plus plus is actually operating on is the pointer s. So s gets incremented by 1 to point to the little e and no longer to the h. Okay, this may be a little tricky to understand here. The plus plus has higher precedence than the star. So the plus plus modifies the pointer s. It does not modify the character star s. Now, this seems like that can't be right. If the plus plus has higher precedence than the star, doesn't that mean that the plus plus should occur first? Well, no. I mean, often it's the case that precedence determines the order in which things are evaluated. But that's not necessarily true. Precedence and order of evaluation are separate concepts. And here, the order of evaluation for a post increment is that the increment occurs after the value of s, that is, after the pointer to h has been used in the expression. All right, so we're incrementing s, but that's not happening until after s has had the star applied to it to get the h that the s is pointing to. All right, so h is displayed, and then we post increment s so that s is now pointing at e. Continuing on with this, we're going to go back up to the test expression in the while loop. Well, is star s still not equal to 0? Yes, star s is the little e, which is not 0. So we're going to drop into the body of the while loop. We're going to display the value of star s, so that's going to display the e. And then we're going to bump the pointer to point to the first L. Well, now we go back up to the test expression in the while, and we ask again, is star s not equal to 0? Indeed, little l is not equal to 0. So this process continues, and I end up displaying the first little l, the second little l, and the o. After the o has been displayed, s will have been bumped to point to the new line. And let's see what happens now with these last couple of steps through our string. We evaluate whether star s is 0. Well, the new line character is not 0. It turns out if you look at the ASCII character set, the new line character has got a value of 10. Doesn't matter. All that matters is that it's not 0. So we're going to display the new line character. All right, we display the new line character. That's going to drop the cursor down to the beginning of the next line below hello. And then we bump our pointer to the next character, and then we go back and look at the while loop test. Now the value of star s is the null character, and the null character is the character whose value is 0, that's equivalent to false, and so at this point the while loop test fails, and I'm out of the DisplayStir function, back in the main function. And since there's no other statement in the main function at this point, the program is over, and I have successfully used DisplayStir to display HELLO new line by stepping my pointer through the successive elements in this string literal. Okay, so this is a very common idiom that you'll see used with strings in C++, is a while loop or a for loop set up to test the pointer to see whether the pointer is pointing at the null character or not. And if it's not pointing at the null character, we typically will make use of the character that the pointer is pointing to, and then post-increment the pointer after we have used that character. All right. So I've talked about strings being allocated in memory and variables being allocated in memory. Of course, your compiled code also has to be allocated in memory somewhere. The final thing we're going to take a look at in this lecture is the memory model used in a C++ program. Basically, memory in a C++ program is divided into 4 chunks or 4 regions. One region is called the code region or the code segment, and that contains all of the executable code, all of the if decisions, the assignments, the multiplications, the loops, blah, blah, blah. And that has a fixed size that never changes while the program is running. The remaining memory is used to contain data, and data is divided into 3 parts. First of all, there's what's called static data, and by static, what we mean is that it's of fixed size, it's in a fixed location, and it does not move around while the program is running. String literals are examples of static data. In other words, the string literal hello over here in double quotes, that gets loaded into static data as an array of 7 chars. It's not modifiable. It's always going to be those 7 chars while the program is running. Now, parameters like s in the DisplayStir function are allocated in another area of memory called the stack. And as you call functions more and more deeply, the stack will grow and grow and grow to account for the parameter and local variables used by those functions that you're calling. As those functions start returning, then the stack is going to decrease in size. Okay, so we've got one segment for code, we've got the remaining amount of memory for data, and we've talked about the static data, which is of fixed size and doesn't move around, and the stack, which grows and shrinks in response to whether we're calling functions or returning from functions. All of the memory that's left lands in this third area for data called the heap, or also called the free store or the dynamic memory. And we'll use the heap shortly when we start creating things called linked data structures, like binary trees and linked lists and things of that kind. So the code and the static data are of fixed size. The stack and the heap do actually change size while the program is running. And they will grow and shrink depending on how deeply your function calls are being nested or how much memory you're allocating for linked data structures. It is possible for the stack or the heap to run out of space, at which point your program will crash. So that is a potential concern. All right, so here we have a diagram showing that the code and the static data have fixed size, the stack and the heap have variable size. And here on slide 18 is our same DisplayStir function with the calling main function that we talked about. All right, so the string here is stored in the static data area. The parameter s is stored in the stack. And in fact, here we have a diagram illustrating this. So when the program runs, the code, which is for the main function, the DisplayStir function, the indirection operator, the put2 operator, the increment operator, all of that code that specifies what's supposed to be done is in the code area. The static data area contains the string literal hello, and also some other global variables like cout for output to the user's terminal and cin for input from the user's keyboard and some other things. When the DisplayStir function is called, its parameter s is created in this area called the stack, and when the DisplayStir function returns, that variable is then deallocated from the stack. Okay, so to summarize this process about how memory gets used, when you execute your program by typing its name and hitting the enter key or by double-clicking on its icon, the code for the program gets loaded into the code segment. Then things like string literals and cin and cout and so forth get created in static data and initialized as specified in the code. After the static data has been loaded into memory and initialized, finally the main function gets called, and that kicks off the behavior of the rest of the program. When you call a function, for example, when the main function calls DisplayStir in our little example, a stack frame, also called an activation record, for that called function gets created on the stack, and storage is allocated for parameter variables and also for local automatic variables that are used within that function. There's also some bookkeeping stuff in the stack frame. For example, there will be storage set aside to contain the return value from the function, if the function does return a value. If you look back at DisplayStir, you'll see that its return type was void, so we don't need to allocate space for a return value for DisplayStir. And then there will be miscellaneous other things like the location in memory where the code should jump back to continue, and so on. Now, parameters, once this stack frame has been created, are initialized with copies of the values that are passed in. Remember that C++ by default is doing call by value. We're passing copies of values in. The argument values become the initial values of the parameters. And then the statements in the function are simply executed from top to bottom. Some of those statements within the function may be local variable declarations. And so those are created and possibly initialized if an initial value has been given. When the function returns, which will occur either because you reached a return statement or because you reached the closing curly brace at the bottom of the function, then all of the local automatic and parameter variables are automatically deallocated from the stack so that that space on the stack is available for some other function to use. And by the way, in the same way that this business of creating symbol tables in Python supports recursion, creating stack frames in C++ also supports recursion. All right, so that's the end of this material.